Hello, hello. Welcome back for another Zephyr release. My name is Benjamin from the Zephyr project. And yeah, Zephyr 4.3 is just out the door. And as always, this will be my great pleasure to walk you through some of the new features, enhancements, highlights of the release. There will be lots of demos. And so if you only care about something or a few things in particular, please do use the time code in the comments to skip through whichever section you are most interested in. Although this time around, the demo is going to be pretty much the same use case, the same application throughout the entire video. So it might actually not be a bad idea to watch the whole thing, because it's probably more relatable in a sense. I will be building something that's more like a real application. So you will see all those new features being exercised in the context of more than just a basic sample. So yeah, something to consider. While you are there, feel free to like the video, subscribe to the YouTube channel. There is a lot happening these days in terms of conferences, meetups, the Zephyr Tech Talks, the Zephyr podcast, which I think might not be a bad idea for you to subscribe. You will get notifications whenever we have new interesting content. And with that, without further ado, let's dive into some of the highlights of the release. As usual, there's a lot. Like there's, I think, close to 800 individuals who worked on this release. We will be going through maybe the top 5 highlights or something, but please do browse and have a look at the full release notes, new APIs and updates regarding the various libraries and subsystems and whatnot. Because yeah, there's certainly a lot happening, new boards, new drivers, and so on. But yeah, let's focus on the top features, the top highlights, starting with something that I will not necessarily like exactly demo, but I want to talk to it for sure, because for the past many years, Zephyr has had support for implementing USB devices. And historically, the stack responsible for this was a bit monolithic, a bit too static in that, like providing all your USB descriptors and so on was something that was very much compile time, very much intertwined between the high-level USB subsystem and the low-level USB controller, like actual device drivers, with the so-called Next stack, which has been in the works for the past couple of years. Things have been re-architected and revamped, and effectively this new stack is now becoming the default in Zephyr. The legacy one will be is deprecated and will be sunset in a couple of releases. And the new stack is allowing you to do things like leverage multiple USB controllers that you might have on your SoCs, including maybe high-speed controllers. It allows you to do configuration at runtime and like to reconfigure and tweak your devices at runtime, and all the ready-to-use USB class implementations that we have for HID devices and mass storage and video and MIDI and you name it. This is all there, and this all works. As a bonus, the Espressif team also worked on adding support for USB device on ESP32, which is something I think many of you were waiting for. So that's pretty cool. All the documentation is out there to learn more about the stack, but my guess is that many of you were already using it probably. So that's for USB. Then, as always, I guess there were changes and improvements throughout the entire stack, all the way from the really low level, and we will be coming back to these things like dynamic frequency scaling or the instrumentation subsystem, things like that. But all the way to the very top, and things that sit on the top of the kernel and the networking stack and the WebSocket implementation, etc., etc. In this case, OCPP, I think, is a great example of something that that was just added and that just works and just builds on the shoulder of giants, I guess I could say. So OCPP is, so it's pretty niche in a sense, but this will make for a good opportunity to show interesting demos. This is like EV focused, as in electric vehicle. So this, in this industry, they have this standard called OCPP for the Open Charge Point Protocol, which describes how an electric vehicle charging station is supposed to talk to and communicate and interface with a backend server, right? And for things like authenticating users with their RFID tags and whatnot, sending telemetry with regards to the actual charging sessions and so on. So this protocol, we now have an open source implementation in Zephyr, which is pretty complete, supports all the different sort of like profiles you have in the standard. This works, I think I mentioned it already, works over WebSockets. And yeah, you have the full documentation for it. And I don't know, let's try and run it on a device, right? There is a code sample available. So let's try and run this and build from there. So the board that we will be using is an ST microelectronics device, STM32N6 something, which doesn't really matter that it's ST. What I needed was something with a reasonably big and large display with an Ethernet controller to do networking stuff. But I mean, as always with Zephyr, the code is fairly portable. So any device, including probably the native simulator, could allow me to run the demo that I want to run. But originally, I will start with the bare bones OCPP sample. So do not expect the GUI to come up because there's no GUI initially, but we will be adding that later. So let's see about this code sample. Let's bring up VS Code and let's just try and build it. So the only minor change that I did is making sure that I would configure the sample so that it talks to my actual server, which actually I forgot to show you. The server is this guy right here, Citrine OS. Citrine OS is an open source project from the Linux Foundation LF Energy initiative. So I know nothing about charging stations and EV software myself, but this open source stack has the merit of being, well, one, open source and super easy to install on a system like Docker containers, etc., etc. I have the stack up and running on my laptop. Had it running in no time. I was able to provision Zephyr charging station, attach it to the location, blah, 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 create the various like connectors and whatnot. And now the only thing that I need is to actually connect an actual device, right? And use this OCPP standard and WebSockets and whatnot to start sending telemetry and to do whatever OCPP does. So let's try and connect my sample application to this server. Again, back to VS Code. So we have the server being configured, and I should be able to just build the sample, and it should just work, right? Like that's the way it works typically with the Zephyr samples. You read the documentation, it tells you what you need. In this case, I need Ethernet, and that should be it basically. Oh, except that it doesn't work. That's a great way to start the video, is it not? What do we have? Looks like, I think some of you will be familiar with this. That's sort of like the dreaded something is wrong in my device tree error. So apparently I misconfigured something somewhere. I don't know what yet. I could probably try and make sense of this. We have documentation explaining what is typically happening here, but in a nutshell, it's likely that somewhere in my device tree for my board or my SoC, something is not properly configured or something is not properly enabled. And this can be painful, except that we have introduced something in this new release that's called DT, as in device tree, DT Doctor, something that you can really easily add to your command line, setting the Zephyr SCA variant to DT Doctor. And what this will now do is look at the compile logs. And when the doctor sees something that looks like it's a device tree error, it will try to figure out like what's the root cause. And so again, like usually it's something that's not correctly enabled in device tree. Sometimes it might be issues with kconfig, but doesn't matter. The tool is there to help you. In this case, it would appear that, of course, my OCPP demo, I need internet connectivity. In this case, on this board, this would be through Ethernet. So I have Ethernet, like I have my code sample that tries to enable Ethernet and stuff like that, right? Like you see it even in the configuration. I try to enable Ethernet, except that my Ethernet PHY device depends on MDIO to be there, and it's apparently there, except that, and this is where it was all just deployed, but it is disabled, and it should not, right? And so that was my mistake. Here, obviously, I introduced the mistake intentionally, but usually it's more tricky to spot the issues with this new tool. It's really like super straightforward. You even have like the exact line numbers where you need to make the change. So we did make the change. We should be able to now build again. Well, actually, let's build again. Let's go and run through the DT Doctor just in case, but DT Doctor this time will likely not see anything wrong. So let's see what we have. We have a successful build, so we should be able to reset the board. This is kind of a special thing I need to do with this board, and then just flash it. Yes, opening a terminal to see what's going on. So we have a terminal, and let's open the browser then, because I think we want to see. Oh, the station just connected already. So that was fast. I knew this was going to be too fast for me to show you that it's not a fake demo, but still have time to show you things like the transactions happening. Apparently there is a slight misconfiguration with the SNTP. Apparently I messed up something there. So the time is wrong, or it's correct in a sense. I mean, SMTP failed, so we don't have the correct date there. But you can see the charging station sending fake transactions. We can even remotely trigger, like pretend that from the server we initiate a session. I don't know, someone would be triggering the session from their smartphone or whatever. So you can see that happening too, starting, stopping. So this all works quite nicely, right? And now stopped. So that's quite nice. So that's for OCPP. Let's move on to some other interesting features. One additional feature is the instrumentation subsystem. In the context of this demo, I will be extending the existing OCPP sample and library. I want to add a GUI, basically, possibly a few other things, but at some point through the process, I might need to understand, like I might have issues that I need to troubleshoot, or things that I want to understand better. So in Zephyr, there are ways to do tracing. Like historically, I think this has been there pretty much since day one. If you want to trace the execution of the kernel and see when context switching is happening and when a thread is waiting on a given semaphore, etc. Like you can instrument or like enable traces, some built-in traces. But here we are talking about something slightly different. Instrumentation subsystem is something that builds on top of and leverages the compiler to at build time instrument virtually all the function calls, so that whenever you enter and exit a function, the instrumentation subsystem is keeping a mental note or like a memory, a note in memory of what's going on, so that whenever you want, you can reconstruct the call graph of a particular piece of your software and your algorithms, and or you can get statistics, more like the profiler side of things. You can get statistics as to how much time you've been spending in such or such a function. So let's try and use the instrumentation subsystem to maybe dig into what's behind some of the functions in my a basic sample, so that I get a better sense of how they work. And yeah, I want to show you how the tool works. Short interruption to set up basically a V2 of the application. I built on top of the existing code sample and added a GUI around it. So this is my charging station now looking more like a charging station, with a GUI showing the connection status and whether there's charging sessions happening, that kind of stuff. And I want to use the instrumentation subsystem to understand better some issues that I have maybe observed in the application. Namely, I have a hunch that the user notify callback from OCPP that I'm implementing in my code might be misbehaving, might be a performance bottleneck, possibly. And so I want to understand better how it works. So I could read through the code. After all, it's my code, I should know. Or another option would be to debug and put breakpoints, except that putting breakpoints into something that's very much real-time and live, like you don't want to put a breakpoint and pause the charging session as it is happening, right? You will have timeouts all over the place, and this probably just won't work. So you want to like basically just put traces, right? And so what I did is that I enabled the instrumentation subsystem. And once you do that, basically you're telling GCC, hey, from now on, every function, when you compile them, add a hook whenever I enter or exit the function. There's a hook, and that hook is basically something that the instrumentation subsystem will use to capture and record what's happening, so that you can later dump that information and analyze the stuff. And so adding this instrumentation at compile time can be pretty expensive. Like effectively, you're turning each function into 3, right? That's your entry, then the function itself, then the exit of the function. If you can afford it, sure, instrument everything, but this adds overhead, right? This slows down the execution. This makes the code larger. Again, each function becomes 3, and this increases the memory requirements for your stacks, right? Because you're stacking up way more function calls, and so here, and you would have to do the same. Basically, that's one big caveat. I've increased every stack size by at least a factor of 2, if not more, otherwise they would just blow up. So once you do that, then you're pretty much good to go. In my case, like by default, instrumentation subsystem would be starting and stopping as you enter and exit your main function. But in my case, it's really that one function that I'm suspecting is misbehaving. So I'm going to be focusing on this one. And then that's it. I've flashed the application to my target. And then how do I interact with the instrumentation subsystem? How do I obtain the data? Well, there's several backends available. Well, not several. There is a UART backend. Over time, I suspect there will be more. But this UART backend allows your host machine to talk to the target over UART and get information, right? So there's a tool that's called Zaru, that actually allows to interact with the target and those sort of like instrumentation commands that it exposes. And so I can use Zaru to check whether my remote target supports instrumentation and whether it supports tracing, profiling, or both. It can be you can customize the behavior there. And once that's there, then I guess I can start trying to extract stuff. And so I will start with a clean session. So I will be rebooting my target right from the PC, again, using Zaru and the instrumentation subsystem UART backend. So target is rebooting. It should be connecting to the server. Yeah, we see that happening. So a new charging session is kicking in, and so now it's probably a good time to see, like, we should have stuff that's being captured, right? And so in terms of profiling, like, what are the top 10 functions where I've been spending time? And yeah, user notify callback, of course, is there. And then there's the split of what's going on. So let's see in more details what's the call graph maybe for this. And so we can actually dump a trace and dump the trace either on the console, but that's not really like easy to do, like automated and to have like a fancy visualization basically. So if I want fancy visualization, I can dump the trace in the Perfetto trace format. That's effectively a JSON file that is ending up on my machine. You're not supposed to read that. Of course, this is the Perfetto UI that's going to be doing it for me. So let's get rid of the charging station for the time being, and let's check out Perfetto. So we have a trace viewer. So it's a web tool. It's a free tool. I think you have it also built in into Chrome, but it's effectively the same thing. And it takes and it eats Perfetto traces, which we just got off of Zaru, opening it. And then we can start diving into what it is we've captured. And so let's zoom right here. And we can actually see that we have a mix of, and this is where I need to focus just a bit to make sure that I'm showing you the right thing. Yeah, let's focus here. See, like if I select something, I can get some interesting information in terms of how much time is spent in every function. So kind of similar to what we had in the profiling before, but we have more, right? We do have the full call graph of what's happening under the hood. And so I could start understanding better that, oh yeah, sure, when I have my simulator simulating meter values, apparently it's taking like what, 200 milliseconds. Maybe that's where the stuff is happening. Well, and so I can start optimizing this way. And this is all like very visual. And if I were to have, which I don't have here, but there could be, of course, multiple threads, and we would see the context switching happening as well. So this is all really cool. Of course, here, very much like a demo / simulated environment. So there's not much of an analysis I want to conduct, but you get the idea. And it's like, as you can see, I hope you can see, it's really easy to enable. Just mind those caveats that I've just mentioned with regards to the overhead, code size wise and performance wise. So you don't want to instrument everything. Most likely. So that's for instrumentation. Now that we have a GUI, I think I want to show you the twister display harness. So that's something that's new. Last time we talked about the power consumption harness. This time, this is all about displays. So basically, you want to automate the testing of something display. Like you are building a driver, and you want to make sure that the driver outputs colors and pixels effectively that are correct, or you are building some kind of high-level application with all sorts of like fancy widgets, like I am, and you want to make sure in your CI/CD and automatically you want to make sure that your GUI doesn't break as you are introducing new features and working on your application. So that's exactly what the twister display harness thing does. And so you basically configure twister to to use effectively a webcam, like using OpenCV, under the hood, well-known computer vision Python-based, C++ and Python-based framework to capture images coming from this video camera that you are going to point at your device, right? Like pointing effectively this camera at the device, and I want to use Twister and OpenCV to capture the quote-unquote fingerprint of a given screen or of a given like snapshot of my GUI, and then capture that and then like store it somewhere, and then later on use that fingerprint as the reference so that in subsequent runs I would compare, and once I do that, I get a score. And if the the reference fingerprint matches the live test, then with a given threshold that you configure, then your test passes. Otherwise it fails. And so, how about we see that in action with our GUI? So I've switched to the Mac just because the recording is easier this way. And what we have here is basically same sample as before. And what I did is that I added a new Twister test suite, or test case rather, that uses the display capture harness. And so what this does is that it uses a configuration file that we will briefly look at to figure out what is the webcam or what is the camera that I want to use, and what are the things that how do I want to test the display. And so in my case, the camera is actually the same that you're seeing right here. So I'm using an IP camera. So right now the device is still doing whatever, but I'm telling Twister, hey, when you need to capture image and like video fingerprints, that's the camera feed that you want to use. It could be a USB camera, all the same. And then I have the configuration of the Twister display harness, where I configure like what is the methods that I want to use to evaluate and to realize and capture the fingerprint of the display. Depending on whether you look for, you're suspecting there will be color inaccuracies, or you care more about where things are physically located, there's a variation of algorithms available. And so you can configure that and then give a weight to all the different types of algorithms. Everything is documented. When do I want to start testing? Maybe 20 seconds in after having ran my starting my application, or maybe I want to start like to capture the fingerprint based on some output on the console, which sort of indicates that, yep, this is the time when I want to test the display. In my case, I haven't like overthought the solution. It captures after a few seconds, and that's it. And there's two modes basically. One is generating the fingerprint that comes first, and then once you're done and you have your fingerprints, then you compare. And so if I am to run the test, so it's basically just calling Twister, right? And I have a hardware map where I describe how should Twister talk. Like whenever there's a test that targets a particular board, like STM32N6, blah, 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 it knows where to find it, how to flash it, etc. And so if I run and start this test, and pay attention also to the to what's happening on the board. So first, it's gonna build the test. Then once the test is ready to be flashed, it will reset the board, flash it, wait a few seconds, and then capture the fingerprint. So let's see. Yeah, board is being flashed. And so the lighting conditions of the whatever camera you're pointing at the device should probably be better than what you have here. You can see my phone actually pointing at the thing. So it should be, of course, you should avoid reflections, etc. But anyhow, we have OpenCV kicking in, capturing the signature of the GUI. signature has been captured, and then doing whatever processing, turning the pixels into a hash, and said hash is what is going to be used later in a second phase when we do the comparison, right? And so I'm going to run the tests again in comparison mode, and let's see if we have a match. Yeah, and again, like lighting conditions should be better than what I have here. You probably want a really, really high resolution camera, because I mean, I haven't tried, but in an ideal world, like you could almost test like pixel perfection. Like if you have a really good high resolution camera, your focus is perfect, then you're effectively looking at each pixel and are able to compare them with really, really good accuracy. Here, again, just for the sake of the demo, it's maybe slightly simplified, but this time around we are running in comparison mode. So signature in progress, let's see if this is a match. 0.98, so 98% a match compared to the original fingerprint. So that's pretty cool. I think that gives you a sense of how far you can push things, right? Like here in my test, I've been super conservative. If the fingerprint only match with 65% confidence, that would be a pass as opposed to a failure. But you can see that like once your workbench or your test bench is properly set up, you can be like really test for pixel perfection and etc. So I think that's really, really nice. This is all based again on OpenCV, which is very much an open source solution. So should you need even more in terms of like other more advanced ways of capturing whatever you think a fingerprint should be, and you want to like extend that, this is certainly a possibility. But I think this is a really nice addition to Zephyr 4.3. So let's move on to something else. What else? We are probably almost through with the release notes. What else? Yeah, the instrumentation subsystem we saw, the CPU load and dynamic frequency scaling subsystems. I think this one is really interesting. So let's start with the easy one, CPU load. There is basically now a one line, like a single API that allows you to get the CPU load, basically looking at all the threads and looking at how much time is being spent in the idle task, in the idle thread. And if you're spending, say, 98% of your time in the idle thread, then it means that you're only spending 2% in the rest. And so your CPU load is effectively 2%. And so that's like one nice API that's now available. I think if we look at my code, sorry, I've actually included it somewhere in the GUI. We have the CPU load. Yeah, I think we saw that before. It's effectively just one call, right? And the CPU load, you obtain a number between 0 and 1. You can do whatever with it. You might have spotted before. I'm actually displaying it on the GUI on the bottom left corner, but I could do other things, including, and that's one thing that's quite nice, and that's making its debut in 4.3, dynamic frequency scaling. So basically potentially using CPU load as a source to automatically at regular intervals, based on how busy your system is, change its move from one power state to the other. And if you have hardly anything to do, then you go in, you can underclock or slow down your CPU and the other way around. So that's a really nice feature, which I'm not really showcasing as part of the demo. This actually requires integration at the SOC level, and so far in the Zephyr 3 is an example that uses basically native sim. So yeah, like this guy right here, it's actually really easy to run, and gives you frankly a really good sense of how things look like. You can describe in device tree, like should you want to use this new mechanism, this new subsystem, and its on-demand scaling policy, then you describe what it is in what is it for you that are the targeted power states. If I am below 50, or rather above 50% load, my power state is 0, otherwise it's 1, otherwise it's 2, and that's it. Granted that your SoC provides the power states, then you can have all these things working automatically under the hood for you, which I think is pretty interesting. So yeah, again, requires SoC support, which I don't think is available in any SoC so far, but the plumbing and the subsystem is there nevertheless. So with that, let's see what else we had in terms of highlights. So we saw DT Doctor earlier as a developer tool, I guess, but we've added a few more, and I always want to make a point of mentioning them because you don't know you need them until you do, and it's always nice to be aware of those because they can save you lots of time. Traceconfig would be for all things kconfig. Say, like in my application, I'm confident and I'm pretty sure that I've enabled the logs and I've set the proper configuration options to enable the logs, and yet they wouldn't show up. It might be that somewhere in the hierarchy of all the files that get pulled in when I build my app, maybe someone is overriding my settings and I didn't realize it. So that's where traceconfig can help you. So if I switch back to my VS Code environment and my OCPP demo, I can really easily and like don't blink because it's going to go really fast. You call westbuild-t traceconfig, and it effectively outputs in your build folder a markdown file that is a snapshot of all your configuration options. So of course, markdown like this is not that easy to look at. Yeah, let's render it. So that's all my configuration symbols, the value they have and why they got it and from where. Like apparently my application init level is 90, and that would be the default value in the kernel. But my OCPP demo, I think, also has display, right? And so display is enabled, and that's something that I've enabled in the sample itself. And back to my log example from before, if I were confused, if for some reason my logs don't show up, why is that the case? Oh, it's my bad. I actually, apparently I disabled the logs right here. That's the line that's responsible for disabling the logs, right? That's the one that came last, I guess, in the hierarchy of all the configuration overlays that got, or fragments that got applied. And that's, the one that's responsible for the logs to not be there. So yeah, really, really easy to use. Use it. And something else which I think is going to be also quite nice in the context of this demo, given that I've been pulling in OCPP and display drivers and LVGL and Ethernet, etc., my application got really big, actually. And so historically, we would have had, and we still have, ways to visualize the RAM usage, RAM and ROM usage of your of an application. And so you can easily get that, I don't know, like RAM and memory wise. I can run the RAM report, which is actually not bad, right? It has colors, etc. But it's very textual. Like at a glance, I'm not going to be able to be like, oh yeah, that subsystem or that area is eating way too much RAM. Maybe I misconfigured the size of a buffer somewhere or a stack. It might not be that easy to spot. So that's where something else kicks in, which is instead of RAM underscore report or respectively ROM underscore report, you would be using the RAM plot and the ROM plot targets. And so under the hood, it extracts the exact same metrics, except that it shows it shows you things in a way more visual way. So RAM wise, where is the bulk of the RAM going for my application? Apparently it goes into that's the LVGL stuff that's eating up most of the memory. That's not surprising, I guess, given that I need pretty large frame buffers. But maybe I can at a glance visually be like, okay, networking takes, and I hope this is not too small for you guys. I think it's all right. But yeah, networking apparently requires 40K of RAM, among which below under 10K would be for the new OCPP stuff. So it kind of gives you a sense of like how much space you need for each thing, and helps you also tweak and remove, disable things that you don't need to save on RAM or code size as well. Like I could of course show the same report for RAM usage and be like and just do the same. And actually, just for the sake of demo, let's briefly look at how much we need for OCPP. So networking requires apparently 66K of flash, but of course I've enabled quite a few things, right? And I have a pretty rich stack with WebSockets being pulled in, and I've been using DHCP client to get an IP address, etc. But OCPP code size wise, OCPP itself is only 8 kilobytes. So that's yeah, that's a really, really nice tool. Very, very interactive. Use it, use it. And with that, I think we're through with when it comes to the main highlights of the release. I may have missed something, so that's why we have comments on YouTube, comments enabled. Please do comment if I forgot anything, or tune in on November the 26th. We will be hosting, and I will be putting the link, of course, in the comments, in a new episode of the Zephyr Tech Talk with Chris and Johan, our release managers, to talk about what's new, what I missed, possibly. Because like there's 100+ new boards, so I'm pretty sure among all those boards there's quite a few interesting things. I know that, for example, the ST Micro guys and NXP as well, and quite a few others actually. There's been a few like some cool things happening on the video front. Some video encoders like H.264 and JPEG and whatever. So really, really cool features. But that's, I mean, you might or might not care about those samples, etc. So do join the webinar. Do subscribe to the channel, and we will be back in slightly longer than usual. Like the next Zephyr 4.4 release is not going to be until April of next year, April 2026. That's something I think you will want to keep in mind. We are moving away from releasing roughly every 4 months to twice a year. Kind of, I think we're basically aligned with Ubuntu. We are going to be releasing in April and October of each year, so only twice a year. Longer, yeah, this will make for an even longer demo next time, I guess. But yeah, that's mark the date on your calendars. The next release is only going to be is not going to be until next April. With that, stay tuned on the channel for upcoming content, and talk to you later. Bye.